Okay, we're going to start Electricity 07, series and parallel circuits. So what I'd like to do is a little bit of a review of our calculations and the components that make up our Ohm's law and Joule's law, and as well make up our circuits. Okay, so the first one is voltage, represented by a capital V in Ohm's law. It is measured in volts, and we represent our measurement with a small v. Voltage is the potential energy of an electrical supply stored as electrical energy. So even though a battery may be chemical energy, what we have in there is a mix of chemicals, right? It is stored as electrical energy. When it comes out of that battery, it's going to be electrical energy. We know that voltage pushes electrons through a conductor. So it's the voltage that pushes current through the conductor. And that conductor may be wire, it may be a human body, it may be the air. There are two types of voltage. We've got DC voltage, which stands for direct current. It's a constant voltage source. An example of this would be batteries or other power supplies, right? Constant power source. So if we have a battery hooked up, it's constant power source. The second type is the AC voltage, or alternating current. AC voltage is oscillating current caused by switching polarities from positive to negative and then back again. So basically what it does is it has a magnet that spins. And if you remember, electrons are attracted to the opposite and they're repelled by the same. So if we have a magnet that's spinning and electrons are moving from the negative to the positive, and we keep changing the polarity, the electrons are going to be attracted and then they're going to be repelled, and attracted and repelled. And that oscillating back and forth is what's making that electrons move. And typically we see AC voltage used in power transmission, so high voltage power lines. And the reason they do that is because the power can move faster and they can move more power that way. And then our homes and our buildings are all fixed with AC voltage, and typically, as you saw when you measured it with the multimeter, it's about 120 volts that are coming into our homes and our buildings. The second component is current, and this is represented with a capital I in the Ohm's law equation. Current is measured in amps, and we designate that with a small a. And current is the flow of electrons through a conductor. So it's the actual flow of electrons. It does not flow through an open circuit. So if you think about the Eastport Bridge coming from Eastport to Annapolis, when the circuit is closed, cars are flowing over the bridge. So we say that that is a closed circuit and electrons can flow. If the bridge is open, electrons cannot flow through the circuit, right? Because cars cannot go over the bridge. So when the bridge is open, cars cannot flow. When a circuit is open, current cannot flow. So think about that analogy with the open and closed circuit and relating it to the Eastport Bridge. Our third component is resistance, and this is represented with a capital R in the Ohm's law equation. And it's measured in ohms, and we show that with the Greek symbol omega. It is the ability to resist or prevent the flow of current. So if we have increased resistance, we're going to have a decrease in current, right? If we want to slow current down for whatever reason, we need to put some resistance in there. And we will see that when we use the LED lights in the next section where we put together some circuits. We will need to use resistors because it's too much current flowing to those LED lights. So we are going to resist some of that current. Resistance can only be positive. It cannot be negative. And then we have Ohm's law, which is the relationship between voltage, current, and resistance. Stated at a constant temperature, current flowing through a fixed resistance is directly proportional to the voltage applied across it and inversely proportional to the resistance. So let's break this down. At a constant temperature, right? The temperature is not going to change. We know that if we increase temperature, that resistance will increase. So we're going to keep it constant. current flowing through a fixed resistance is directly proportional to the voltage applied across it. So if we increase voltage, we are going to increase our current. And then it goes on to say, and it's inversely proportional to resistance. So if we increase resistance, we're going to decrease the current. So here's some examples to show that. So current in amps is directly proportional to the voltage in volts. So if we are going to increase our voltage to 20 volts, we are going to have to double our amps. So you can see that in the equation. 5 amps equals 10 volts divided by 2 ohms of resistance. We double our voltage to 20 volts, and we can now see that our amps are going to also double to 10. Current in amps is inversely proportional to resistance. So again, in the equation, 20 volts equals 10 amps times 2 ohms of resistance. Assuming that that voltage stays consistent, we're using a battery, okay? So the voltage is staying consistent, direct current, and resistance increases, so we double our resistance to 4 ohms. Our amps are going to decrease, right, by 50%. So we doubled our ohms, and we are going to have our amps. So we went from 10 amps down to 5 amps. Again, you guys probably remember this little visual here, and it's just demonstrating that relationship, the direct proportional relationship as well as the inverse proportional relationship between the 3 components. The fourth measurement that we used in Joule's law was power, and we represent that with a capital P in the equation. It's measured in watts, shown with a small w, and power is the amount of energy that is produced or absorbed in a circuit. So, for example, we can produce the energy, and then anything that's in the circuit is going to absorb the energy. So a lamp or resistor, that is going to actually absorb that power. So we have a voltage source, like the battery, and then we have a lamp which is going to absorb it. So again, Joule's law is power equals volts times current. We need both current and voltage present to have power. So some examples, if we have an open circuit where the switch is open, again, think of the bridge, right? If the bridge is up, cars cannot flow over the bridge is open, so we don't have any current. So in that situation, we have voltage but not current. So if we multiply by 0, our answer is going to be 0, correct? That's simple elementary school math. So we have no power. Same thing with a short circuit. In this situation, we've got current, but we do not have voltage. So again, if voltage is 0, our power is going to be 0. And again, you remember these visuals. This is just kind of a help in calculating both Ohm's law and Joule's law. All you need to do is cover up the one that you're looking for, and you can see what you need to do with the other 2 components, if you need to multiply or you need to divide. And then this is just a pie chart taking the 2 equations and using substitutions, the different ways that you can calculate the amps, the volts, the ohms, and the watts. And then what we can do is we can use these equations to verify our circuits. So in this diagram here, we have a series circuit. And the reason we know it's a series circuit is because electricity only has one path to follow. Okay? Remember, it's going from the negative to the positive. So our electrons are moving through this way. And I just clicked on that. Okay, so in this situation, we've got volts of 24 volts. We've got amps of 2, or current of 2 amps. We have resistance of 12 ohms, and we have power of 48 watts. So using our calculations, we know that current times resistance is volts. So 2 amps times 12 ohms gives us 24 volts. That checks out. We know that power is current times volts. So again, 2 amps times 24 volts equals 48 watts of power. So we know, and we can double check our numbers in these circuits when we're calculating them. Okay, I'm going to stop right here and create another video for series circuits. That was the review video. We'll get into series circuits and calculating our voltage, our amps, and our resistance in a series circuit.